Okay, so in this lesson, we're going to talk about a new factorization which is given by P times D times P inverse, where P is the matrix of linearly independent eigenvectors of A, and D is the diagonal matrix. So before we get started, let's see how good the diagonal matrix is. So basically, to get the eigenvalues and eigenvectors, we have to solve the characteristic equation, or in other words, d minus lambda I is given by 2 minus lambda, 0, 0, and 3 minus lambda. And we have to solve for the determinant of d minus lambda I equals to 0, but this equals to 2 minus lambda times 3 minus lambda, and the root of this polynomial, or the root of this equation, should be lambda is 2 and 3. So when lambda is 2, d minus 2I equals to 0, 0, 0, and 1. The solution set for the homogeneous equation should be x2 is 0 and x1 is the free variable. Or we get the eigenvector corresponds to lambda equals to 2 as 1, 0. Similarly, when lambda is 3, d minus 3I equals to negative 1, 0, 0, and 0. So this gives you the solution set for the homogeneous equation equals to 0 and x2 as a free variable. So this gives you x2 times 0, 1. So we get the eigenvector corresponds to lambda equals to 3. So far so good. But the power of having the diagonal matrix is when you calculate the power of the given matrix. So, well, let's first consider d squared, which is given by 2003 and 2003. So this equals to, so the first, or the 1 entry equals to 2 squared, and we have 0 and 0, and we have 3 squared for the 2 entry. And if you calculate d to the cubed, then this gives you 2003 times, I guess, 2 squared, 003 squared. That equals to 2 to the cubed, 0, 0, and 3 to the cubed. So, well, if you see the pattern, we have d to the 10 equals to, I guess, 2 to the 10, 0, and 0, and 3 to the 10. So basically, the powers of the diagonal matrix is simply the power of each entries. So d to the k equals to 2 to the k, 0, 0, and 3 to the k. So let's look at this example. So this example was given in the previous section, and we've calculated the eigenvectors and eigenvalues of the given matrix. So here, P is the matrix which was built by the eigenvectors as the column vectors. So 1, 1, 0, negative 1, 0, 2, and 1, 1, 1 were the eigenvectors of the given matrix. And the corresponding eigenvalue is 2 and 2 and 3. So in this case, we have A times P equals to P times D. Or in other words, you can write A equals to PD times P inverse. So let us quickly check whether this matrix equation is true. So first of all, A times P is given by 4, negative 2, 1, 2, 0, 1, 2, negative 2, 3 times 1, 1, 0, negative 1, 0, 2, 1, 1, 1. So this gives you, I guess, 4 minus 2 equals to 2. And negative 4 plus 2 is, I guess, negative 2. And the third one should be 3. And this one should equals to 2, I guess. And negative 2 plus 2 equals to 0. 2 plus 1 is 3. And we have 2 here. And negative 2 plus 6 is 4. And 2 minus 2 plus 3 gives you, I guess, simply 3. So this was the left-hand side, AP. And if you do the P times D, then this gives you 1, negative 1, 1, 1, 0, 1, 0, 2, and 1. And if you multiply this to 200, 020, 003, then this equals to, well, 2, negative 2, 3, 2, 0, 3, and 0, 4, and 3. And you can see that these two matrices coincide. So we get AP equals to PD. So if you have that kind of factorization, we can calculate a to the 100 as we did in the diagonal matrix. So let's look at this. A squared equals to A times A. But if you apply that factorization, well, that gives you A equals to PD times P inverse. So if you apply that again, we get this. And here, you can see that these two gives you the identity matrix. So that equals to this matrix product. Or in other words, multiplying identity is nothing. So we get PD dP inverse, or this equals to PD squared times P inverse. If you do the same thing for A to the cubed, then this equals to A times A squared. Or in other words, that equals to P dP inverse times, well, we got PD squared times P inverse. And this equals to, again, PD and P inverse times P equals to the identity. So we get this. Or if you simplify this, then we get PD cubed P inverse. So if you keep this procedure, then what can you tell about A to the 100? Well, there is a pattern here, right? So this should equals to P times D to the 100 times P to the inverse. So the pros of this one is, well, we have D is a diagonal matrix. We can calculate D to the 100 really in 1 second, right? So we can calculate A to the 100 very fast. But unfortunately, we cannot always factorize the matrix into diagonal matrix. So let's discuss when we can do this kind of procedure. So a square matrix A is said to be diagonalizable if A is similar to diagonal matrix, or in other words, A is given by PD times P inverse, where P is an invertible matrix and D is a diagonal. So to form the invertible matrix, we need to have n number of distinct eigenvectors. So if there is a basis v1 through vn of r to the n or c to the n consisting of eigenvectors of A, then A is diagonalizable. But if that is not the case, then we cannot diagonalize the given matrix. So not all n by n matrices are diagonalizable. So I gave you sort of an example of this in the previous section. So if the matrix A is given by 2, 10, and 0, and 2, then this is not diagonalizable. Or in other words, this is not similar to the diagonal matrix, which is given by 2, 0, 2. So you want to pause the video for a moment and check it by yourself. So basically, to summarize the argument above, an n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. When you diagonalize the given matrix, P, the columns of P are n linearly independent eigenvectors of A, and the diagonal entries of D are eigenvalues of A that corresponds to and respectively to the eigenvectors in P. So the order really matter in this case. And moreover, if you have n linearly independent vectors, then we can form a basis for R to the n. So let us practice how to diagonalize the given matrix. So suppose that A is given by this 3 by 3 matrix. Then basically, our goal is to build A equals to P dP inverse. So we have to find the eigenvectors and eigenvalues to diagonalize the given matrix. So to find the eigenvalues of A, we have to calculate the determinant of A minus lambda I, or this equals to the determinant of Well, I guess 2 minus lambda, 0, 0, 1, 2 minus lambda, 1, negative 1, 0, 1 minus lambda. So if you expand along the first row, then this gives you 2 minus lambda times the determinant of 2 minus lambda, 1, 0, 1 minus lambda, and the rest are simply zeros. And this certainly equals to 2 minus lambda times, well, I guess 2 minus lambda times 1 minus lambda. So if you let this equals to 0, then we get lambda is either 1 or 2. So in this case, we have multiplicity 2 for lambda equals to 2 and multiplicity 1 for the first eigenvalue. So the next thing you want to do is to find the linearly independent eigenvectors of the given matrix. So when lambda is 1, well, eigenvectors are the solution set for the homogeneous equation a minus I times x equals to 0. So we have to calculate the null space of this matrix. And if you subtract I from A above, so you get, I guess 1, 0, 0, 1, 1, 1, negative 1, 0, 0. And if you RREF this matrix, then you will get 1, 0, 0, and 0, 1, 1, 0, 0, 0. So the solution set for the homogeneous equation should be x equals to, so x1 is 0, and x2 is negative x3, and x3 is a free variable. Or this gives you x3 times 0, negative 1, and 1. And for lambda equals to 2, a minus 2I equals to, I guess 0, 0, 0, 1, 0, 1, and negative 1, 0, 1, or negative 1. And if you RREF this matrix again, then you get 1, 0, 1, 0, 0, 0, and 0, 0, 0. So the solution set for the homogeneous equation is, I guess, well, x1 is negative x3, and x2 and x3s are free variables. So you get x2 times 0, 1, 0 plus x3 times negative 1, 0, and 1. So we get eigenvectors as 0, negative 1, 1, 0, 1, 0, and negative 1, 0, 1. So the first one corresponds to lambda is 1, and the other two corresponds to lambda equals to 2. So once you get all the eigenvectors and eigenvalues, then we can form P and D using these two things. P is given by a matrix of column vectors of eigenvectors. So you can build P by O negative 1, 1, 0, 1, 0, and negative 1, 0, 1. And D corresponds to the diagonal matrix of diagonal entries as the eigenvalues. But here, you have to match the column vector of P with the corresponding eigenvalue. So for example, the first entry should be 1, and the second and the third one should be 2. So diagonal matrix should be 1, 2, 2 in the diagonal entries, and the rest are zeros. Then once you have that, we have a relation AP equals to PV. So if you multiply A times P, then this gives you 2, 0, 0, 1, 2, 1, and negative 1, 0, 1. And P was given by 0, negative 1, 1, 0, 1, 0, negative 1, 0, 1. So if you calculate this, then we get 0, 0, and negative 2. And I guess it is negative 1, 2, and 0. And the last row should be 1 and 0, and I guess 2. On the other hand, P times D equals to, so we have 0, negative 1, 1, 0, 1, 0, negative 1, 0, 1, times 1, 0, 0, 0, 2, 0, 0, 0, 2, and this equals to 0, 0, negative 2, and I guess negative 1, 2, and 0, and 1, 0, and 2. So we get AP equals to PD. Okay, so if you have the matrix B, which is given by in this way, then B is not diagonalizable. So let's pause the video and find out the eigenvalues and eigenvectors before I give you the solution for this problem. Okay, so basically we have B as the upper triangular matrix. So you can certainly tell that the eigenvalues are main diagonal entries. So lambda should equals to 2 and 3. And first of all, when lambda is 2, then B minus 2i equals to this matrix. And the null space of this matrix should be x1, 0, 0. Because x2 and x3 are 0, where you get the eigenvector corresponds to lambda equals to 2. And similarly, if you calculate B minus 3i and take the reduced row echelon form, then that gives you the solution set for the homogeneous matrix equation as 0, 0, and x3, where you get an eigenvector corresponds to x3. So here we can observe that there are only two linearly independent eigenvectors. Or in other words, we cannot build the matrix P, so B is not diagonalizable. So here, one thing that you want to note is that the dimension of the eigenspace is of lambda I is always less than or equals to the algebraic multiplicity of the given eigenvalue. And it's always greater than or equals to 1. And this is because if you have an eigenvalue, then that means you can find at least one corresponding eigenvector. So in the above example, 2, lambda is 2, has multiplicity 2 in the characteristic polynomial, because the characteristic polynomial is given by 2 minus lambda squared times 3 minus lambda. So the problem appears in this part. So if you compare this with the previous example above, so basically 1 had the multiplicity 1 in this case, and 2 had multiplicity 2. So in this case, we had the proper number of eigenvectors to form the basis for R3. So if I rephrase the sort of diagonalizability, so the given matrix A is diagonalizable if and only if, so the dimension of the eigenspaces corresponds to each eigenvalues should be the same as the algebraic multiplicities of the given eigenvalues. Okay, so let's pause the video and try to see whether the given matrix C is diagonalizable or not. So let's work on this problem together. So first of all, we know that C is given by triangular matrix. So the eigenvalues are given by 2, 6, and 1. And if you have 3 different eigenvalues, then we can find 3 different linearly independent eigenvectors corresponding to these eigenvalues. So which means we get 3 linearly independent eigenvectors that spans R to the 3. So C should be diagonalizable. And if you really do the calculation, then you will get the result like this. So really we get 3 different eigenvectors corresponds to each eigenvalues, which means C is diagonalizable. So in other words, if n by n matrix has n distinct eigenvalues, then that matrix has to be diagonalizable. So this is the last example of today's lecture. So let's pause the video and verify whether the given 4x4 matrix is diagonalizable. And if possible, diagonalize the given matrix. Okay, so how do we begin with this problem? So basically, you want to begin with the characteristic equation. So we have to solve the determinant of a minus lambda I equals to 0. But this equals to negative 2 minus lambda, squared times 2 minus lambda squared because we have lower triangular matrix. So if you let this equal to 0, then we get lambda is either 2 and negative 2. So for the both cases, the algebraic multiplicities are 2. So we hope to find 2 eigenvectors corresponds to 2 eigenvalues respectively. So first of all, when lambda equals to negative 2, then we have to solve for a minus negative 2 times I. Or in other words, this equals to, I guess, 0, 0, 0, 0. So the first two rows are 0. And 24, negative 12, 4, and 0, 0, 0, 0, and 4. So if you take RREF of this matrix, then this gives you 1, negative 1 over 2, and 1/6, and 0, 0, 0, 0, and 1. So the solution set for the homogeneous equation is given by, well, x equals to, so the x1 should be 1 over 2 x2 minus 1/6 x3. And x2 and x3 are free variables, and x4 is 0. So if you separate the variables, that gives you x2 times 1 over 2, 1, 0, 0, plus x3 times negative 1 over 6, 0, 1, and 0. So if you let this one as v1 and that one as v2, then v1 and v2 form a basis for the eigenspace corresponds to negative 2. Similarly, when lambda is 2, well, we have a minus 2 times I equals to, so now we have negative 4, 0, 0, 0, 0, negative 4, 0, 0, 24, negative 12, 0, 0, 0, 0, 0, and 0. So if you take RREF again, then this gives you, I guess, 1, 0, 0, 0, 0, 1, 0, 0, and the rest are all zeros. So this gives you x equals to, well, first two entries are 0, and x3 and x4s are free variables. So this gives you x3 times 0, 0, 1, 0 plus x4 times 0, 0, 0, and 1. So again, these two vectors are basis vectors for the eigenspace corresponds to lambda equals to 2. So if you build matrices using all these things, so for P equals to, well, V1 and V2 and say V3, 0, 0, 1, 0, and the last one, 0, 0, 0, 1. And D equals to the corresponding eigenvalues. So the first and second columns are negative 2. And the third and the fourth one should be 2. And the off-diagonal entries are just zeros. Then we get AP equals to PD. Or in other words, you can factor the given matrix A into PD times P inverse. So the theorem 13 summarizes what we have learned for this section. So suppose that A is given by n matrix with distinct eigenvalues, lambda 1 through lambda p. Then for each lambda sub k, the dimension of the eigenspace is less than or equals to the multiplicity of the eigenvalue of lambda sub k. And the matrix A is diagonalizable if and only if the sum of the dimension of the distinct eigenspace equals to n. And this happens if and only if the dimension of the eigenspace for each lambda k equals to the multiplicity of lambda k. And if you can diagonalize the given matrix, then we have n number of distinct eigenvectors to span each eigenspaces. So if you collect all the vectors in the basis for the eigenspaces, then you can form the eigenvector basis for R to the n.